now probably is simpler and also lighter than Aaron's one, so maybe you can relax a little bit before lunch. So I'll tell you about robust optimization strategies for the analysis of protein dynamics in model fitting. Okay, you know me already. You can find more about my work in this site. The motivation of the methods I will describe here start with the problem of protein alignment. You all know that during evolution, proteins have changed their sequence by suffering mutations, but many times the sequences preserved their structure. So today we have many organisms that have different proteins that have proteins with different sequences, and these sequences fold into similar structures. And the protein alignment problem is to when you obtain a new structure by with experimental data, you want to know, for example, what is the function of this new protein, and you align this structure to a database of protein structures, and you may find out that this structure is very similar to other structures that were already determined, and by doing so, you can infer function and other properties of the structure. Okay, so this is the original motivation of the methods I will present here, but actually the applications that I will show are not these applications, because these applications are not of particular interest to you. So I show you some other applications in which I correlate the methods we have developed for this problem to molecular dynamic simulations. So I will tell you a little bit about protein alignment, the basics of protein alignment. Structural alignment is done essentially by two steps. First, if we have two structures, so here is structure blue, structure orange, we have to determine generally which is the correspondence between atoms between the two structures. Now, generally, if we have two proteins, the two proteins may not have even the same length, so we don't know which atoms of one structure correspond to which atoms of the other structure. So we must determine which is the correspondence between the atoms of the two structures. Once we have determined a correspondence between the atoms, we can use this correspondence to structurally align these two corresponding atoms. So I have chosen this correspondence between atoms, and then I have moved one of the structures in order to fit the best way possible this structure with the corresponding atoms in the second structure. So this was not good. So I realized now I have a new relative orientation structures, and with this new relative orientation, I can suggest another correspondence between the atoms, okay? And with this new correspondence between the atoms, I can do a second structural alignment, and then, okay, obtain something that looks like a good alignment between the first structure and the second structure. So, in most methods of structural alignment, we have these two steps. One step is to determine the correspondence between atoms. The second step is to do structural alignment, and that can be done iteratively in order to obtain a good, actually meaningful alignment between the two structures. Okay, we have to measure the alignment quality in some way. So we finished our method. We obtained some overlap between the structures, and I want to measure this alignment quality. You are very used to use the root mean squared deviation as a measure of mobility, and it is used also as a measure of alignment quality. However, by itself, the root mean squared deviation cannot be used alone as a measure of alignment quality, because, for example, if we are dealing with problems in which we don't know how many atoms of the first structure must be assigned to how many atoms of the second structure. So, for example, if we assign a single atom of the first structure to a single atom of the second structure, we just overlap their centers of mass of these atoms, and we have a system, we have an alignment with a zero RMSD. So, of course, this doesn't mean that I have a good alignment. So the RMSD by itself is not a good measure of alignment quality. And this is a common issue in protein alignment strategy. So usually one wants to define a structural alignment score that incorporates both the quality of the alignment in the structural sense and the number of atoms that are being alignment in the same equation. So we use something like this, which is a sum over every pair of atoms of my assignment. My assignment may or may not include all atoms of the proteins. So a sum over every pair of atoms of my assignment of something of this form, in such a way that if I have many pairs of atoms, this sum is greater. And then if I have small distances between the pairs of atoms that were assigned to each other, the score is also greater. So this score increases for larger assignments and increases for smaller distances. Such a way that, okay, if I have this case, for example, will give me a small score because n is small. So this is something that can be used as an alignment, a measure of alignment quality in structural alignment. So we have these two steps in structural alignment. One is determine the correspondence between atoms. The other is to obtain the structural alignment. We define a score of somehow looks like this in order to measure the quality of my alignment. And I want to solve these two steps, the determination of the assignment and the structural alignment, in such a way that is nice and efficient. So just this I won't enter into details, but when I want to determine the assignment within the atoms, for example, if I have these two structures and they are in a previously determined position in space. So the position of the two structures in space are given, okay? They are fixed and given. And given the position of these two structures in space, I will set, okay, which is the best assignment between the atoms of the two structures for this given orientation of the two structures in space in order to maximize my score. Okay? This has an analytical solution, a numerical solution, but global solution that can be obtained by dynamic programming. That means, I don't know how many of you know and have ever solved a problem with dynamic programming techniques. Okay, one of you. So, but the idea is quite simple. So imagine we have this relative orientation of the structures fixed, and okay, if I assign atom 1 to atom 1, I measure the distance between these atoms and I have the score, the corresponding score, and I put this in a table. So atom 1 assigned to atom 1 gives me a contribution to the score of 1. If I assign atom 1 to atom 2, this gives me a contribution of score of 0.8, because atom 1 is farther from this atom 1 is farther from this atom 2 than from this atom 1. So the contribution to the score is smaller. If I assign atom 1 to atom 3, here I have a contribution of 1.6. If I assign atom 1 to atom 4, I have contribution of 1. These weights here are only qualitative. So I fill one matrix of this size, and then I fill another matrix, which is called the cumulative score matrix. And this cumulative score matrix is like that. So I want this alignment to be sequential. So proteins are sequence of alpha amino acids, which are sequential. So I don't want that my assignment starts with the first atom of the first protein may be corresponding to the first atom of the second protein. Then the third atom of the first protein may be corresponding to the 10th atom of the second protein. I don't want now that the second atom, so I went back on the first protein, be able to correspond to the 15th atom of the second protein. So in that case, my alignment would not be sequential. Generally, in most cases, protein alignment is sequential, so this makes the problem easier. Okay, so
how do you decide the values for I have D is
D0. This is a scaling problem. D0.
You could use the same value
for everything. Yeah. D0 is a fixed value only to scale the distance in some reasonable sense in terms of the scale, the size of distance between atoms in your protein. Okay, this is used as 5, and this 20. Generally we use 20 here, 5 here, with D in angstroms, and this is okay for proteins. Okay, it's just empirical finding. It's not really determined. It's just a matter of scaling and unit conversion. Okay, so we fill this matrix that says which is the score assignment between the two structures. Now we fill a second matrix that we start to fill it iteratively, and I say, okay, let's start from the end, because my assignment will be sequential. So the last atom of my first protein must be necessarily assigned. I will assign the last atom of my first protein. So I assign the last atom of my first protein, atom 4, to the atom of the second protein that gives me the best score, 3.8. Okay? So I see here that assigning the fourth atom of the first protein to the fourth atom of the second protein gives me the best score for this atom of the first protein. Okay? So I say, okay, my alignment starts here with the atom 4 being assigned to the atom 4. Okay, this alignment must be sequential. So the atom 3 of my first protein must be assigned either to atom 3, atom 2, or atom 1. I have already assigned 4 to 3, so I cannot assign 4 to 3. I like 3 to 4. Which is the best assignment for the third atom of the second protein. Here I'm doing the other way around. I'm choosing which is the assignment of the atom of the second protein which best contributes to the score within the atoms of the first protein. So if I go to the third atom of the second protein, I see the best contribution is to assign atom 3 to atom 2. So I have the first assignment is 4 to 4, the second assignment is 2 to 3. Okay? And then I cannot use any of these assignments anymore because this one is already picked. So the next time I will try to assign atom 2 of protein of the first protein, and I see, however, that if I assign atom 2 of the second protein to atom 1 of the first protein, I get a total score, a cumulative score. I'm summing the scores here, a cumulative score of 9.6. However, if I assign atom 1 to atom 1, I have a cumulative score of 9.8. And that defines my overall best sequential alignment possible. Okay?
The number of atoms in the structure first.
It's the same. Nothing happens. Similar, you have a non-square matrix here, and you could do exactly the same procedure. It's exactly the same. So there is absolutely no problem with that. This is the methodology that is used for sequence alignment in DNA and proteins and everything else. So this is, I think, okay. This is not the most important. This is part of what I'm talking here today. But okay, it's good since you are students. This is a very important technique in bioinformatics, and it's good that you know that it exists. Okay, this was developed in 1977, and it's a very classical result. Okay, so with this method, you can obtain, for a given orientation between the two structures, you can obtain the best assignment, globally best assignment between atoms of the two structures. Okay, for a given orientation. Okay, so I have, for a given orientation of the two structures, the best assignment between atoms of the two structures. Okay, so now I have, given the correspondence, given the assignment that I obtained using dynamic programming in the previous step, there exists an analytical solution for the rotation and translation of one of the proteins that minimize the root mean square deviation. Okay, So given that my assignment is 4 to 4, 2 to 3, 1 to 1, there is a solution, an analytical solution. This is what every package does when you do structural alignment in VMD, etc., etc. There is an analytical solution which consists in overlapping the centers of mass and solving a simple eigenvalue problem that will give you, given this correspondence between atoms, will obtain which is the best rotation then translation of one of the proteins that minimize the root mean squared deviation between the two structures, given the assignment. Okay? So, okay, the natural algorithm, which is called, this is the natural algorithm in my point of view, this is called structural algorithm. It was developed by Subiá and Levitt in 1993. It involves using dynamic programming in the first step to obtain the best. In this case, this is a bijection, a sequential bijection between the two structures for the present position of the atoms, and then given this assignment, you obtain the minimum root mean square deviation by standard alignment. So this is repeated. Now, with the new orientation between the structures, you do again dynamic programming to obtain a new assignment, and you repeat this iteratively until convergence. Okay? If converged, because this does not necessarily converge. Okay? Did you get the overall idea of what structural alignment is? Okay. So now we see this problem with a different point of view, which is our contribution to the problem, which is to see structural alignment as what we call a low order of the optimization problem. Low order optimization problem. Now, the problem is the same. However, we'll look at it with a different perspective. So we have two structures, structure A, structure B, and we can, of course, between these two structures, we can have many assignments, different assignments of atoms of one structure to atoms of the second structure. So, for example, here I assign atom 1 to atom 1, atom 2 to atom 2, 3 to 3, 4 to 4. I can have another assignment different here, a different assignment here, a different assignment here, another different assignment here. Okay? There are many, many possible assignments between the atoms of the two structures. And the thing is, let's look from this perspective. For each of these assignments, there is a function, a continuous function, okay, which is the score as a function of the rotations and translations of one structure relative to the other. Okay, given the assignment, or I know which atoms correspond to each other atoms in the other structure, I can move one of the structures relative to the other in order to see, okay, how the score varies, the overall score varies, as I move one of the structures relative to the other for this given assignment. Okay? There are many functions like this. For each of these assignments, there is one function of the score as a function of rotations and translations. So for this assignment, there is one function. For this assignment, there is another function of the score as a function of rotations and translations of the other protein. Okay? What do we want to maximize? So we get for each assignment a different function of the score as a function of rotation and translations. I overlap all these functions, and what I want to do is to maximize the maximum of all these functions. Okay, so I overlap. Here is one function corresponding to the movements of relative movements of the structures in one correspondence. For one assignment, here is the function of the score relative to the movements. For another assignment, the objective function of my optimization problem, the thing I want to maximize, is for each rotation and translation, the maximum of all functions. Okay, so this is the objective function I'm trying to maximize. If I obtain the maximum of this blue curve, which is the maximum of all concurrent functions, I will have the best alignment possible between both structures, both from the point of view of the assignment and from the point of view of the relative orientation between the two structures. So the objective function of my optimization problem becomes this blue curve, and this is a problem that consists in maximizing the maximum of a set of concurrent functions, okay, which is equivalent of minimizing the minimum value of a set of concurrent functions. That's why the problem is called low order value optimization problem. Okay, this is a new problem in the optimization community actually. Okay, so one interest here for you, this is a detail, but this is interesting result from the point of view of optimization, is that this objective function may be non-smooth. That means it does not have continuous derivatives, because in these intersections you have non-smoothness of the objective function. However, this non-smoothness is benign, because if you are applying a numerical method to solve this optimization problem, if you reach one of these points, you can choose the gradient of any of the concurrent functions, and you can use that gradient to proceed your optimization procedure with conjugate gradients, for example, and reach a local maximizer of the function. So it's a particular case in which we have a non-smooth function for which can be optimized by any of the many standard smooth optimization methods that exist in the literature, which are very practical and efficient. Okay, you can use the derivatives of the problem in spite of the fact that the function is non-smooth. And this is quite interesting from the optimization point of view. Okay, this for you, this is only a detail. Okay, so how does it look like, the process of solving this optimization problem now from the perspective of low order value optimization? We start with a given orientation, or relative orientation between the two structures, and here it is. You see, for a given rotation and translation, that means for a given relative orientation between the two structures, I have here, I'm in this point. This is a relative orientation between the two structures. I may know, for example, using the dynamic programming, how to compute from this relative orientation between the two structures, which is the best correspondence that I can compute using this orientation. That means in this graph to go from I'm in this point, the relative orientation between the two structures, solving the problem of obtaining the best assignment between the two structures means finding which is the curve that maximizes this function at this point. So, using dynamic programming, I obtain this point. Okay? Now I use a smooth optimization method to solve this problem. To solve it, here I have a smooth function which can be maximized by conjugate gradients or any other smooth optimization method. And what does it mean from the point of view of this image? Maximizing this function means going that way. So I go, for example, I conjugate gradients will take me there, or the Newton method will take me there, and I obtain this point, which is the maximizer of this function, which is the function that corresponds to the rotations, and that is the score as a function of rotations and translations for one given assignment between the atoms. Okay? Now I have a new set of rotations and translations. Now I can, using dynamic programming, for example, obtain which is the maximizer of the score, which is the assignment that maximizes the score for this new rotation and translation. This takes me to this new point. Now I recognize which is the function of rotation and of the assignment that is maximizing the function now. And now, okay, I go again, iteratively, apply again my smooth optimization method to maximize this function, and I obtain the maximum. Okay? Here we are converging to the global maximizer. This is not necessarily true, but we can converge to local maximizers at least. Okay, this is everything you can expect from optimization methods.
Always true.
Okay. Sorry?
Type of maximization always work.
Yeah, it always converges.
Pathological cases.
No. This is proved to converge. I mean, if you use a convergent method for the smooth part, there are many algorithms that are proved to converge in the smooth part, you necessarily converge to a critical point of the true objective function, in this case, the dashed line, the dashed curve here. Okay? This is proved to converge. Okay? Very well. So, the optimization problem, optimizing this problem, solving this problem in terms of low order of optimization means using dynamic programming to find the best score for the present relative position of the two structures, and then instead of minimizing the root mean square deviation, which has nothing to do with the score, we use any of many continuous and smooth optimization methods that have proved convergence properties and so on to solve the smooth optimization problem of maximizing the function for its concurrent function. So this is convergence and leads to a more robust, a better and more robust algorithm for structural alignment. Okay? Very well. Until now, I'm talking about structural alignment. This is all developed in thinking about structural alignment, but it has had some interesting consequences for our work in molecular dynamic simulations, and which are actually simple applications of this method. So, which is the easy problem of structural alignment? The proteins are the same. Okay, this is what we do every day when you are checking how is the mobility of your protein in your simulation. You are doing structural alignment, but the protein you are alignment to the other protein. One protein is one protein in one step of your simulation. The other protein is the same protein in another step of your simulation. So the protein is the same. However, it may have different conformations. If the protein is the same, the assignment between the atoms, it's not a problem, because you know, okay, this atom corresponds to the same atom of the other structure. There's no problem there. So what we do every time is to minimize the root mean square deviation and plot those graphs of root mean square deviation as a function of time. Look how my protein goes on. You can see how your protein is diverging from the initial structure, for example. Okay, so this is a typical example. We use the structural alignment to analyze mobility in a simulation. So we have a sequence of structures which were obtained during the simulation a long time, and we do alignment using a simple technique of structural alignment VMD does, which minimizes the root mean square deviation for the structure, and we obtain this plot, blah 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 blah, and we obtain a picture of the mobility of the structure. This is what we all do. Okay? Very well. Now I will think the problem in another way, using what I was telling you before. Okay? Instead of simply doing the structural alignment as we are used to do, I will do the following. Given any orientation of the structures, okay, I get one frame of my simulation, I get the other frame of my simulation, they are more or less overlapped, of course, and given this orientation of the structure, I will not simply align my two proteins using everything. I will choose which are the 80% for this orientation of the structures. I will choose the 80% best aligned C alpha atoms. So, do you see what I'm doing? I'm getting one structure, the other structure, and I will see, okay, I will compute the distance between every pair of atoms, between the two structures, which are the same structure from different frames of my simulation. I will see which are the 80% smaller distances. Okay? So I choose these 80% best aligned atoms, and I align again, however, not considering, okay, not considering the 20% worst atoms in my alignment. So I forget that my protein has 100 residues, I consider only 80 residues, and I do the alignment thinking that my protein has 80 residues. This defines a rotation and translation, a relative rotation and translation between these two structures. Okay? Given this new rotation and translation, the protein now has moved for aligning these two, these 80% best aligned atoms. Now the protein has moved. Now I compute again the individual root mean square deviations for our atoms. Now the 80% best atoms are other 80%, not necessarily the same, which allows me to do another alignment for another 80%. And I repeat this iteratively. Okay, so I choose 80% best aligned atoms, align this considering the 20%, move my whole protein, and compute again the individual distances to choose again 80% best aligned atoms and do this iteratively until convergence. This is a particular case of the problem I was telling you before. It's proved to converge, and it converged quite quickly. If you try, it's very easy to implement this, by the way. Converge, and you obtain something. Okay, let's see what's something. So why this is the same thing as before? We had before many possible assignments here. Now the number of assignments is much lower because we know that atom 1 must necessarily correspond to atom 1 in the second structure, because they are the same structure from my simulation. However, I want to choose the 80% best aligned atoms. So the kind of different assignments that I have are not anymore permutations. Are simply, okay, I assign atom 1 to atom 1, but this one was not between the best, so I will not assign atom 2 to atom 2, and then I will assign atom 3 to atom 3, atom 4 to atom 4, and I will not assign atom 5 to atom 5. And this is another possibility. I will assign 1, 2, 3, but 4 and 5 will not be assigned. For each of these assignments, there exists a function of the root mean square deviation as a function of rotations and translations. Okay? You understand that? So for this other assignment, which is the assignment of a subset of my protein, there is another function of rotations and translations. I will do a minimization of the minimum root mean square deviation. You see, it's the same problem as before, just simpler. Okay? The function I'm minimizing is this one. Now is the minimum of a minimum of functions. And I will repeat the process iteratively until convergence, and everything will be the same. So now, instead of the score, I have the root mean square deviation. Each assignment is chosen by simply picking the closest 80% atoms of my structure, and the process is exactly the same as before. This is, given a rotation and translation, pick the best alignment 80% atoms. This gives me a new assignment. Now, minimize the root mean square deviation. This is standard alignment that DMD and every other package does. I have a new rotation and translation. This gives me a new set of 80% best aligned atoms. And from there, I minimize again the function and obtain, which is the, look what I'm obtaining at the same time. The best root mean square deviation, the lowest root mean square deviation, for the best 80% aligned atoms at the same time. Okay? Is for a subset of 80% aligned atoms, this is the best possible root mean square deviation. Both things at the same time. What kind of results this provides me in terms of interpretation of what can I do? So this is I just repeated the mechanism, it's the same thing. This is the algorithm, it's the same thing. What kind of result this can provide that help us in the interpretation of the mobility of a protein in a molecular dynamics simulation. So that was my typical graph. That was the picture of the typical mobility of my protein in a molecular dynamics simulation. And I have the root mean square deviation as a function of time, and it oscillated around 2 angstroms after some while. Okay? Now my procedure gives me two different root mean square deviations. It gives me the root mean square deviation of the 80% best aligned atoms, and at the same time, I can compute that, which is the root mean square deviation of the 20% worst aligned atoms. Okay? And I had not to choose a priori which are the two groups. Okay, this is automatic from the algorithm. But now I have a root mean square deviation of the more flexible region part of the protein, and I have a root mean square deviation of the less flexible region part of the protein. The root mean square deviation of the rigid part of the protein oscillates between 1 and 1.5 angstroms, less than that. The root mean square deviation of the more flexible part of the protein goes up to 3 angstroms. Now, the same picture, now I overlap the alignments of my structures along my simulation, but now the alignment was done only for the 80% best aligned atoms. What I see is a different picture from the previous one, where I can clearly discriminate which are the rigid parts of the protein and which are the mobile parts of the protein. Okay? So this the use of this technique, which in the case of molecular dynamics simulation is pretty simple because it simply choose the a subset of best aligned atoms and do standard to alignment, and this iteratively. This is quite simple from the point of view of molecular dynamics simulation. Gives me a way to look at my simulation, to the mobility of my structure, my simulation, in a way that highlights what are the parts of the protein that are actually moving. Okay. Okay, from now. Now I will use this for another thing, which are called model fitting. And let me see, I'll try to do, what I'm trying to do here is to propose to experimentalists mutations that will improve the stability of a protein. Okay? So what I'm going to do. In principle, this is the thermodynamic cycle involved. I have a native folded protein, and I have a native mutant protein. I have a native unfolded protein, and I have a native unfolded, mutant unfolded protein. Okay? Experimentally, what we do is to unfold the native protein, unfold the mutant protein. Okay? And if the mutation, if the difference in free energy, if the delta G of this process is greater than the delta G of this process, my mutation has stabilized the folded structure. Okay? Okay, we know by molecular dynamics simulation that this is very hard to do. Okay, even we can do free energy perturbation to obtain the free energy associated with this mutation here. We barely can do any simulation that represents the unfolded state. So doing this, actually from a quantitative point of view, using molecular dynamics simulation is very hard. So I'm not interested in solving the problem from the rigorous point of view. I'm interested in proposing to the experimentalist something. Okay? So what we'll do, I'm going to do the following. So I will think about this thermodynamic cycle, and I will do very simple simulations. I will do one simulation of the native folded protein. I will do very short simulations of every possible folded mutant protein. That means if my protein had 300 residues, I will mutate every residue 20 times and do 6,000 simulations. Each simulation, I don't know, 50 picoseconds long. Okay, very short simulations. And I will do simulations representing the unfolded structures, which there is some evidence in the literature that we can use small peptides that have the same sequence as the local sequence of the structure as a model of the unfolded state. Of course, this is very approximate. But then I will do 6,000 simulations of peptides representing local structures of unfolded protein. Okay? And I will use only potential energy parameters, electrostatic interactions, and van der Waals interactions to compute what would be, with many commas, the difference in free energy between the two states. So given that I have the potential energy of this residue with the environment here, the potential energy of this residue with the environment here, the potential energy of this residue with the environment here, the potential energy of this residue with the environment there. And I can compute the differences and suppose that the entropy doesn't play any role. And so my potential energy parameters from these fast, simple simulations, barely equilibrated, I will compute something that I will call the free energy difference between the two states. Okay? The question is, does this work? Who bets it does work? Who bets it does not work? Come on.
It works.
Okay, we're wrong. Okay? Of course it does not work. Okay? Well, you cannot suppose that you are just, otherwise, what would be the point of using those sophisticated methods for computing free energy? I mean, it does not work. Of course not. Okay, so it does not work. We are glad to see it does not work, otherwise our job will be, no, it would be good as well, but okay. But anyway, it does not work, so this is the correlation between the experimental delta G values and the calculated delta G values. Essentially, there is no correlation, and we have a standard deviation between the calculated and the experimental delta G's of almost 5 kK per mole, which makes any proposal absolutely unuseful. Okay? Particularly, we see that the models fail. This model, very simple model, fails miserably for many mutations. And of course, this fails miserably because for many mutations, a simple potential energy approach and those simple simulations is not a good enough model. Okay? So it does not work. However, I will think from the low order value optimization perspective and remove outliers. So instead of, I just give you a grasp of this in order you to that you see that it's the same thing. Now, before I was adjusting rotation and translation so that the model coordinates fit the reference coordinates. Okay? Now, instead of doing fitting of coordinates, I have a model to fit. I have a predicted value that is a function of some parameters of my simulation. In this case, the electrostatic potential and the van der Waals potential. Okay? So I have to adjust the parameters of this function, a and b, in this case linear, which is easy but could not be linear. I must adjust the parameters of this function so that the predicted values fit best the experimental data. Okay? This is typical. Okay, I have a model, I have the experimental data, I have some parameters from my simulation, I want to fit the experimental data using the parameters of my simulation, I have to solve this problem. Okay? However, I will use the low order value optimization approach. I will choose. I will invent some parameters here from these first parameters. I will choose the best 80% best data, okay, which is better fitted by the model. Now I will redo the fitting. I will adjust my model again, disconsidering the 20% I removed in the first step. I will compute the individual standard deviations for all data again. This will give me a new set of best 80% data, for which I will fit the model again, and do this iteratively until the 80% best data is the same. See, it's exactly the same as before, except that I'm not aligning structures, I'm fitting a model to experimental data. So, yes.
So when you say removing outliers, it doesn't mean to identifying the outliers? Or?
Yes, it does mean identifying the outliers, but automatically. The only thing I must say to the algorithm is that I want that it considers 20% of the data as outliers. Not exactly that. I say to the algorithm, disconsider 20% of the data. Okay? And automatically, by choosing the best data, fitting again, the model will converge to something that will give me, as in the case of the structural alignment, a solution that is the best model fitting for the best chosen 80% data at the same time, as was the case in the structural alignment. Okay? So, okay, this is in computational terms essentially the same thing as before. So it also converges. This is a low order value optimization problem. It's proved to converge quickly, and so on. Which is the result? The result is that if I do my comparison with all the data, I have this almost no correlated data. If I remove 20% of the data, now there is a correlation. If I remove 60% of the data fitted has an even greater correlation with experimental data. If I look at the quantitative analysis, I have a standard deviation of almost 5 kK per mole for 100% of the data, but if I remove 20% of the data, my standard deviation goes down to minus than 1 kK per mole. And if I get 60% of the data, I go to 0.5 kK per mole. And below 1 kK per mole, I can suggest things to experimentalists. Okay? So the thing is that model is not, that simple model was not very bad. The problem was that it was very, very bad for a fraction of the data. Okay? So that means that, in generally, at least for 60% of experimental data, for this protein, of course, okay, this is work in progress. For this protein in particular, there is at least 60% of the mutations that improve the thermostability of the protein only by simple energetic reasons that can be computed from the electrostatic and van der Waals potential. So I can use this data. If I suggest a new mutation and I use the model I have fitted, I have a 60% chance of obtaining, of giving a suggestion to the experimentalist that has a 0.5 kK per mole relative to experimental value. Okay, and this is very, very useful from the practical point of view. Okay?
And is there some sort of pattern of what is?
Yeah, okay, it could be. It could be. In the perfect case, no, one could do, this is a good question, no? If I choose, for example, a percentage of the data that I'm choosing, and this is the standard deviation of the quality of my model. Here, I choose all data, so I have a large standard deviation of the model. And here, if I choose only 1 point, I have a 0. Okay? In a perfect case where the outliers are clearly identifiable, what do you have? You have 0, 0, 0, the model is perfect, and for, I don't know, 73% of the data, now I start to have points that cannot be fitted by this model. Okay? I have points that cannot be fitted by this model, I go up. Okay? This is the ideal case. Okay? Of course, no problem falls down in something like this, but generally what we have is something like this. So, not zero here, of course, but if you have a really good model for a small fraction of the data, and the same model is very bad for the other fraction of the data, you can have something like this. In practice, you get something in the middle. That depends on your data and your model.
Are there typical mutations in the standard deviation?
It could be. I don't know. I have not analyzed it from that point of view yet, this data. This is quite new. Okay? But it could be done. The thing is that you can, exactly, this is an interesting problem. This is an interesting question from the point of view of the physical nature of what you obtain, because once you have this analysis, you can say, okay, exactly, which is the physical nature of the mutations that do not fit into a simple energetic model? Which are the physical nature of the mutations that do fit in the energetic model? And this kind of thing can be done for every kind of model and every kind of fitting. This is only a particular example. Okay, yeah.
How would you discern, suppose you had data that was truly just randomly distributed, that there was no structure.
Okay.
I imagine you could use this technique to say like, oh, you know, if I use less points, if I just pick the ones that happen to be close to the line,
this is some kind of validation. Okay, you can do. If there is really not structure, then your distribution will be always something random here. So, but okay, your fitting will pick the atoms that are in the diagonal. That's true. Okay, but this is a lower bound for the quality of your alignment. You can do that with random data and see, okay, if the data was truly random, what would be my result? And now I have my real data. What is the actual difference between my fittings with my real data relative to truly random data? Okay, so that can be used to validate the quality of the model and the quality of the removal of the outliers. Yeah.
So what you are saying is that if you perform another rotation, you have like 60% of probability to be right
Yeah.
and 40% to be wrong.
Yeah.
It's not the same as, it's in a coin.
Yeah. To go down to 0.5 kilo-K per mole, yeah. But that's very good, If you try to propose mutations to experimentalists in order to actually, in practice, improve a protein from the point of view of thermal stability, for example, if you just look at the structure and propose a mutation, your chances of being right are much less than 50%. I bet you. Okay. So and also this is a very simple model. I could improve a little bit my simulations in order that my calculations could be a little bit better in such a way that this percentage could be greater. That depends on the model. Here I'm only talking about the concept of the model fitting. Okay. So essentially that was I was going to tell you. So what I wanted to show is that structural alignment that we usually do is not the best way to see the structural variability of a protein or for the structure in an MD simulation. It's better to do an iterative procedure removing the more mobile parts in order to actually discern which is moving and what's actually moving and what actually is not moving. These strategies of robust alignment allow the automatic distinction of mobile versus rigid structures, and the root mean square deviation of each part of the protein allows us to see with more clear eyes the molecular motions. And this is done without extrapolation or overinterpretation of the MD data. I mean, you are only aligning, you're doing nothing more than aligning the structure. So what you are seeing is actually the mobility of the structure in your simulation. It's not an overinterpretation of the data that use, for example, normal modes and so on, that you can infer things that didn't happen in your simulation. In this case, no. This is simply the alignment, and what you see is what you actually got in your simulation. Okay? And the same robust strategies can be used into model fitting. And I think this is quite important, actually, as an idea, that every time we develop a model, we may be developing a model that we expect this model to be able to explain our data. That may happen. If you are a theoretical physicist, for example, you usually develop a model that you want it to explain our data. However, when you go a little bit to complex problems, many times you develop a model which not necessarily will explain our data. It will explain a fraction of the data. And in this case, when you are going to fit that model to your experimental data, you have to use one of these strategies to see which is the fraction of the data that's explained by your model. Otherwise, you may think your model is not worthwhile at all, but that's not true. It actually explains well a fraction of your data and not the rest. Okay? For your knowledge, from the point of view of the protein alignment problem, database and so on, if someone wants to align proteins using command line arguments and a fast algorithm, this is available online and can be downloaded, it's free and so on. And the more theoretical considerations on these optimization problems were published into papers that are visible only for the mathematical community, Journal of Global Optimization and Mathematical Programming. Okay, this is what I was going to say. More information you can get on my site. And I thank the invitation and financing of all these institutions. Okay, thank you. Yeah?
I have a question that relates to your flexibility of the protein. So you can also use root mean square fluctuations to find out which regions of the protein are more flexible than the others. So I was wondering if you have compared your results from RMSD, your algorithms to the results from root mean square fluctuations. Do they match?
What do you mean exactly? Here I had the fluctuations of the structure computed with the standard way. Okay, so you see this is the structure. You see, okay, this is very typical. The structure oscillates relative to the initial structure around 2 angstroms. This is very typical from a protein dynamic simulation. Okay, but we actually used this in 2 papers in order to analyze with more detail the mobility of our structures, and we see that the less flexible region part of the protein oscillates much less than the more flexible part of the protein, and you can actually discern which is the part which is actually mobile in the protein relative to other part that it's a rigid core. Yeah.
We can also do calculations wherein we can describe how much a particular residue has fluctuated over the course of the simulation.
Exactly, you could do that.
That match up with
for a particular residue, this is kind of tricky because that depends of the reference of your alignment. Because if you align a single particular residue through your simulation, you will only see the mobility of the side chain. I mean, this can be tricky. You know, if you want to analyze the mobility of a particular residue, you have to choose with very care which is the reference you are using for the alignment, because you align one part of the structure. For example, I want to know the mobility of the active side of the structure, so I align this helix and I see the mobility of the active side relative to this helix. This can be done, but it could be related to that. But for example, if you want to know the mobility of this residue, for example, the active site is here, the active site is here, and I see that the active site is not mobile and the other regions of the protein are mobile. And in the previous image, I could not see that clearly, this effect. Any more? You're hungry? Let's go. Thank you.